Hello, and welcome to optimization of the Firefly algorithm for use in image tracking. To start off, let me show you a short demonstration. Here, the user selects an input movie file, in this case a .avi file, and an output folder in which they'll output the object tracking output data. Now, you just click the start button and ready to go. As you can see, a small window shows up. We just click on the center of the object that we want to track and enlarge it to a rectangle. And then here we go. So as you can see the little kernel that we're tracking. You can see the results, and you can see the fireflies as they are being generated. They converge to an answer, and basically that answer is then shown on the middle graph. The program, of course, works on live footage too. So here's a good example. In this live action scene, we have a character who is not only in low lighting settings, but also has a shaky camera going on and lots of movement. So watch how this turns out. So back to our discussion. As you probably know, object tracking is the tracking of an object over a sequence of images. There are many ways to accomplish this, but in this particular way we're doing it through optimization. That is, we take the initial target, then make several candidate solutions, then we decide which of those candidate solutions fits our old initial state best, which really means the similarity function is calculated. In this case, the similarity function that we're using is the Bhattacharya coefficient of the color hue of the histograms of our kernels. So in this case, we take the kernels, we find the color histogram, so then we take the Bhattacharya coefficient between those two of the candidate solution and the known state, and use that as light intensity. So how do you find the best candidate solution? To this end, the Firefly algorithm is used. In this algorithm, several candidate solutions are produced, and the less fit, those with a smaller similarity function, move towards those with a higher similarity function, plus some random movement for diversity. And in this way, the candidate solutions will converge to a local maximum solution. And in this case of object tracking, the state vector is, of course, object position and size. So once the Firefly has found the other Firefly with a much larger light intensity, it moves towards that Firefly given this following relationship. The program itself was written in Visual C++. The reason why it was done in this way as opposed to like MATLAB or something like that, or Python, is that the Visual C++, I'm using the OpenCV library, which allows for basic image processing to be done by that. So all of the unique stuff, all the Firefly algorithm, all of the Bhattacharya coefficient is done by myself, but like the actual taking in the video and displaying the windows is done by the OpenCV, while the Microsoft MFC application takes care of all the GUI stuff. So in this way, I can just focus on the actual application at hand. And speaking of that, also a great thing about C++ is its object-oriented nature, in that way that the Fireflies perfectly align with the object-oriented paradigm, because each Firefly is its own little object with its own state and its own functions that can deal with the other ones, and it really, really fits. But as you can see, the true problem of optimization is that the optimization has to be optimized itself. the parameters of the optimization, the gamma component, which controls how the fireflies move towards each other, and the alpha component, which controls the random movement around the fireflies, all have to be tuned in such a way that the object tracking is optimal. So that is the purpose of my study, and what I found is, through studying lots of different combinations of those two variables, is that the alpha component should be larger. It's the random movement around the actual initial state vector that causes you to find the solution, mostly being because when you have video, the object movement is very minimal. So what you're going to find is the actual best solution is closer to the object than it is away. So that random movement helps the candidate solutions find the optimal solution around this object, wherein the large gamma component, all that really does is just move the solutions that aren't going to work anyways towards the optimal solution. So at the end of the day, we're collecting 5,400 different data points of different parameter inputs and judging the output value. So the output parameters we judged were the number of generations, the best intensity value, and the worst intensity value. Now the best and the worst intensity value, those come from testing for the convergence of the fireflies. So as in when the intensity value, which of course is the Baudrillard coefficient, when that is above a certain threshold, we call that's the F best. That is a good value, and if the other fireflies are within a certain distance, we can consider that converged. Now F worst is the worst value that we'll actually consider. So if it is above that certain threshold, the very worst one is above a certain threshold, we'll consider that guy to be good enough, and we'll converge on that. So those are our two test conditions for convergence. And what we're doing is we're testing what those are, and we're testing the number of generations it takes. So the speed, and then the actual accuracy of the object tracking, because the object is going to have the middle one right there, the one with the 0.04 gamma coefficient higher than the 0.2 alpha coefficient, when it looks more like the object that we're actually looking for, and the Baudrillard coefficient is higher. So I have here the number of generations, the best intensity, and the worst intensity, and for each one of the parameter combinations that I've chosen, we've done 150 times of those particular chemicals in different test cases. So what's going to happen is take the average of all those to see how the parameters affect the output. And the results are, you can see right here, those are the best in three scenarios. So we have the best number of generations, so that means the minimal number of generations, so it works the fastest. The best intensity, so that means the maximum Baudrillard coefficient. So with that being much higher, that means it's a much better graph, and we have, of course, a maximum worst intensity, so even the worst firefly is still pretty high. So as I said, saying right now, the middle one seems to have the best results, most reliable. It doesn't lose the target as often as the other does. Just the best overall parameters. So of our experiment, that's the one that was the best. In conclusion, the parameters themselves, what the optimal value is, depends on what you want to get out of your object tracking algorithm. You can go for more accuracy with more random data that will find the best solution, or you could go for faster converging rates, having the higher gamma parameter. So in the end, it depends on what you really want to get out of it.